Hello, class. So today we are going to do an exercise in binomial random variables lesson, and this lesson is on identifying binomial variables. Right, and so let's get started. So um, let's see. So before we start, before we dive into the question. It will be best if we talk a little bit about what a binomial distribution is, right? So binomial random variables, right? Binomial distribution of binomial random variables. Okay. So what satisfy a binomial random variable? So what are the conditions? So I wanted to say and tell you that we usually use this acronym called BINS, right? BINS. And B stands for binary. Now, binary, we know it means two, right? So, two, it means success or failure, right? So, it means it could be heads or tail, right? Success or failure, up or down, male, female. So it just basically means two, right? Two things, two possible outcome. All right, that's probably more like it. Two possible outcomes. Now, I refers to independence, right? So the variables are independent of each other, right? Um, okay, so the trials, you call it the trials are independent. So let me give you an example. So if you, for example, when you flip a coin, say 5 times, and how many times the do heads come up? So it could be 0 times, could be one, could be two, could be three, could be four, could be five. And each time if you flip a coin, it's considered a trial. And each time if you flip a coin, the coin itself, the trial itself is independent. So the very first flip is independent from the second flip. That means the probability of the first flip being a head or a tail doesn't affect the probability of the second flip. So that's the meaning of independence, right? The trials are independent. Now n refers to number of number of trials, right? So a previous example, I said flip the coin 5 times. So the number of trials is fixed, right? It's five. Um, so number of trials is fixed. All right. So S refers to probability of success, right? The probability of success. So for example, flip five, flip 5 coins, right? Or flip one coin 5 times. And X is the random variables of the number of heads. So if you look at this example, right, is this a binomial random variable? So first of all, let's look at, is it binary? So yeah, there are only two possible outcomes every time you flip a coin, right? It's either a head or a tail. So check, yes, binary outcomes. Is it independent? Are the trials independent? Are the coins independent? Each flip, are they independent from each other? Yes, they are. Number of trials is fixed. So here, number of trials is 5. So the probability of success. So let's say if you want to find the number of heads, we know that the probability of heads is 0.5, right? 50%, 0.5. Each time you flip a coin, the probability of heads do not change. It's always going to be 0.5. Check. So it satisfies a binomial random condition. So this is a binomial random variable. So, with that said, let's dive in. So, let's go into this question. Which of the following are binomial random variable? Right? So, if you look at the very first one, um, Miss Clover, not Clove, Glover writes the names of her 30 students on individual pieces of paper and randomly selects the names of 5 students from a hat. And let M equals to the mean number of letters in the first names of the students. Wow. So is it a binary outcome? Um, no, because you're selecting 5 names from a hat. It's well, yeah, it's not that doesn't give you binary outcomes at all. Uh, or you can look at individual pieces of paper and say that piece of paper can will it be selected or will it not be selected? Yeah, maybe that's another way of looking at it. And how about not fixed number of trials? 5, right? You just need 5 papers from the 30 papers that you put in the hat. That's okay. And then I is in independent. Mm, yeah, it doesn't affect, right? Each time if you go in and select a name. But what is interesting is this: the probability of success changes every time you pick up a paper, right? So, for example, the if you have a hat, right, a container, right, and if you go in and pick up a number, right, pick up a paper. So you have a piece of paper that says a student's name, right? Then that name is ready use, which means that there are only 29 more names left. So that first person to be chosen, the probability of that student being chosen is 1 over 30. Second paper being chosen, it will be 1 over 29. So the probability of success changes. So it's not A, right? A is not the right way to go. It's not a random variable. It's not a binomial variable. So how about A is not B? So Sadio randomly chooses a student from his class and asks them if they are left-handed. He stops once he finds the first handed person. So this is not a binomial. In fact, this is a geometric because the number of trials is not fixed. Because what if the very first person he asks is left-handed? Therefore, the n stops at 1, right? The trial stops at 1. What if it takes him 2 people to find the first left-handed person, or 3 people? So the trial is not fixed. How about Amelia? C. Amelia rolls 5 fair die, and D equals to the number of die that shows a value greater than 3. Number of die that shows a value greater than 3. So is it binary? So a die can show greater than 3 or not greater than 3. Now, is it independent? So roll 5 dice, and each die can be greater than 3 or not greater than 3. And D is the number of dies that shows a value greater than 3. So it could be 0 or it could be all 5 of those dies. So is B binary? Yes, right? Greater than 3 or not greater than 3. I, is it independent? Yeah, probably it says fair, right? Fair dies. So they're independent. N, fixed number of trials because there are only 5. So, and greater than 3, probability greater than 3. A fair die has 6 sided, it's a die has 6 sides. So greater than 3 could be 4, 5, or 6, right? 4, 5, or 6, so it's 0.5. So it's fixed. The probability of success is 0.5 in this case. So, all right, good. We chose the right one. So, Let's look at another question. In a game involving a standard deck of 52 playing cards, an individual randomly selects 7 cards without replacement, right? You do not replace those 7 cards. So if you draw 7 cards out, there will be only 45 cards left. Okay, so let y be the number of king drawn in that 7 cards. So is y a binomial random variable? Now, so each card, if you draw the 7 cards, each card can, well, it's a binary outcome because it can be a king or it doesn't, or it's not a king, right? So it's binary. Um, how about I? Is it independent? Well, each card should not affect the other card. And so, but it actually does if you think about it. And I'll elaborate that a little bit when we go to the probability of success part. And fixed number of trials, yes, it's fixed because it's 7 cards. But the number of success, the probability of success of whether a card, whether the card is king or not, it's it's kind of, it will change because there are only 4 kings allowed in a standard deck of cards, right? And if you are drawing cards without replacement, now the probability of success of a card, right, of probability of kings, sorry, probability of kings, right? So the probability that the first card is a king will be 4 out of 52. But once that card is taken out, the probability of the second card to be king, let's say the first card is not king. So you still have 4 kings left in there somewhere. But it's out of 51 cards now because the first card is already thrown out. So in this instant, the probability of success is not, right? It's not independent, right? It's not independent. We have this. Each trial isn't being classified as success or failure. Well, it is. Fixed number of trial, there's 7 of them. So in this case, well, there isn't any option for probability of success. So probability of success is going to be linked with the independence rule, right? So the trials are not independent. Okay. All right. Sweet. Let's do another one. Juanita is a basketball player who makes 75% of all free throws she attempts. Right, so she makes 75% of all free throws she attempts. We can assume that the results of her free throw attempts are independent from each other. Good, it satisfied the independence condition. Which of the following choices are binomial random variable? So Juanita shoots a series of free throw until she makes a free throw. So the number of trials is not fixed. So this is not a binomial random variable. Juanita shoots a series of 5 free throws. So the n is fixed. And m is the number of free throws she makes. Yeah, all right. This should be, yep, this is binomial. Juanita shoots a series of free throw until she makes 5. So number of trials is not fixed. All right. So, all right, let's do this quickly. Based on previous data, an electronic manufacturer knows that 2% of its computer processors are defective. So we now know the probability of failure in this case, or probability of success. All right, failure because it's defective. Probability of success is 2%, right? So that's fixed. Suppose the manufacturer randomly selects these processors until one is found with a defect. Wow. So we select these processors until one is found with a defect. That doesn't sound like a binomial. It sounds like a geometric. Geometric is you go through, right, the number of trials is not fixed. You do it until the first success come about. So that's geometric. So here it's not binomial because the number of trials is not fixed. So is D a binomial variable? No, it's not. Why? Because even though it has a fixed the probability of success, um, even though it has the first part A, right? Success or failure, it's either defective or not defective. Okay, but that's not a problem. There is no fixed number of trials, right? There's no fixed number of trials. Okay, all right. So if you have any questions, let me know. Hope everything is fine. All right, see you next time.